All right, here we go. All right, anode bevel and focal spot. A lot of this information you should know already. There aren't too many new concepts in here, just a few. So we'll obviously get to those in a second. As you should already know, I hope, there's an anode, part of the tube, and there's a part where the electrons will hit the anode. That is the actual focal spot, wherever it actually bombards the anode. But, and this is the part that I hope you knew already, but maybe you didn't, but just in case, there is an angle to this anode, right? And as you know, the whole thing is spinning, so it's kind of actually coming out at you and back into the wall. So it's spinning really quickly, and we'll talk about why it spins, although I think you know why it spins, because it has to do with heat, right? Today, we're going to talk a lot more about this angle and what it means for focal spot, and also what it means for anode heel effect. Okay, another thing about this angle is the angle may change, but whatever the angle is, it is. In other words, you can't change the angle. Like, there's no mechanism in the tube that makes it change its steepness. So the only way to get a different angle anode is to buy a different tube, right? But we're going to talk about different angles today, but realize you can't actually change any one angle yourself without purchasing a new tube. And we should already know, because we did the lab on this, that when you use a smaller focal spot, you will get better spatial resolution, right? The sharpness will increase. That can be measured with a line test tool like you see here, or the ones that we've been using in the lab. And we know that the difference is pretty small to see. And you might even question, as I talked about in the lab, why we even do this if you can't physically see it, but maybe some people can. And you never know when, you know, a little bit better spatial resolution somehow allows some physician to see something that they might not have seen, and that could literally be the difference between life and death and a prognosis for someone. Who knows? Point is, smaller focal spot, whichever focal spot it is, whether the actual focal spot gets smaller or the effective focal spot that we talk about a little bit later in more detail gets smaller, spatial resolution increases. So you got arrows going, you know, in two different directions. Focal spot down, meaning getting smaller, spatial resolution goes up. And when it comes to spatial resolution, a lot of times we intertwine it with this thing called penumbra, which we've defined before is this sort of blur, right? So the whole object, you know, goes from one side of the penumbra to the other. But what we would like to do is try to reduce that penumbra, which would then make the umbra, which is the middle part. So the penumbra is the fuzz and the umbra is the middle. If we shrink this penumbra, the umbra itself gets bigger, right? So essentially, if we drew a circle around this, okay, and this umbra here is another circle inside, right? What happens is by reducing the penumbra, the umbra actually grows. So this inner circle extends, right? So there is no overall magnification change, right? You're still going from one side to the other, but you would have less penumbra and more umbra, right? It's kind of like if you have a donut and you change the size of the hole, make it bigger or smaller, but the outside is still the same, right? It's still the same distance from, you know, one, I was going to say sprinkle, but, you know, one side of the donut to the other, right? There's a diagram related to this near the end. So we'll go over this concept one more time. And it's proportional, not just proportional in that both arrows go up, but it's directly proportional, which means if you double the size of the focal spot, the penumbra gets bigger, which is worse. Not just bigger, double. Double one, the other one doubles. So the actual focal spot is the physical portion of the anode that actually gets strucken. Strucken, is that a word? That is actually gets struck by the, yeah, I knew I should have changed the proportion of vodka in here. You guys just think I'm drinking, tea, right? Yes, no. You can test it. There's nothing bad in here. So this is the part that is actually having a physical interaction with electrons. Okay, actual focal spot. And we know that's the source of most of the heat, right, in the tube, is those interactions. That's the reason why we spin the thing really fast. That's the reason why we play with the diameter, too, of the anode. Sometimes it's a bigger or a smaller frisbee, so to speak. The effective focal spot, though, is not really a physical thing. You can't touch it. Right? The definition is, and every time I think of this, especially since the new Amazon commercials came out where the boxes have they talk and they have a smiling face on them. You must have seen them because unless you have no TV. Right? Because Amazon is Amazon. And maybe they can give back to us some money that they don't pay taxes. I'm a big Yank supporter. I haven't given him any money yet, but I'm thinking about it. So the definition of the effective focal spot is it's viewed from the perspective of the image receptor. So the reason I mentioned the whole Amazon thing is I picture this image receptor with little eyes, kind of receiving the photons and kind of looking up, right? And the effective focal spot is always, always, always going to be smaller than the actual focal spot. Okay. And the reason for that is because of the angle or the bevel on the anode. Right. So if we go back here for a second, right? I don't know which one of these is working best. If this is our actual focal spot, so filament is down here, this is our actual focal spot, right? If we draw a line from here down and a line from here down, you will see that this width here is much different than the cathode ray beam width here, right? So that is because of the angle of the tube. And why that happens is based on what is known as the line focus principle, right? Right. So if you make the effective focal spot smaller or the actual focal spot smaller, spatial resolution increases. And the spatial resolution increases because the focal spot, the effective focal spot, gets much smaller, right? It goes from around a centimeter, I think I have more exact numbers on the next slide, down to 10 times or more smaller. So we're at 1 millimeter, right? And that's with the large focal spot. So let's get to the next slide, which has better numbers. Okay, so let's take the right side for a second. So our large focal spot, right, is going to lead to an effective focal spot of 1 to 2 millimeters. And this is based on the average angle of most tubes. Average angle, right, they can change, is around 15 to 17 degrees. So we're talking this angle here, right, is 15 to 17 degrees. And this angle is made from sort of the tube is here, so it's perpendicular and down, right? So that's where you get this kind of angle in here. So that angle, if it were to be on average between 15 and 17 millimeters, using a large focal spot, that will decrease our effective focal spot down to 1 to 2 millimeters, right? That's much smaller. And if we use a small focal spot, we're actually down to less than a millimeter, half of a millimeter, 0.5 to 1 millimeter, right? So as we just said, the smaller the effective focal spot, the better the spatial resolution. Utilizing a much smaller actual focal spot would cause too much heat. So if we try to narrow the beam on the actual focal spot, so if we tried to make this smaller, right, so that this was like this, right, then sure, right? I mean, this would end up getting much smaller too, right? But a lot of heat, right? Because we'd be concentrating the beam on a much smaller part of the anode. And even though the anode is spinning around, you know, theoretically, we're just still going to get more heat. So that's a problem. So we're limited as to, you know, how small we could make the actual focal spot, right? And also because it's linked to the filament, you know, if we have a filament that's too small, we won't get as much intensity of radiation that we want. We won't be able to boil off as much thermionically boil off electrons, which is why we have two focal spots to begin with, a small and a large. And we use the large because we need more radiation and we don't want to waste more time heating up the smaller one for a longer period of time where it might just snap. That's the other fear. So yeah, a much smaller focal spot, like we were saying, is due to that angle, right? And that whole principle is known as the line focus principle. So here's a nice example, right? Notice the actual focal spot is the same, right? Because width of the right side and the left side are the same, right? That's our cathode ray beam. But the angles are different. This one is close to a normal angle, right? And this one is rather large, and we see the difference in that our effective focal spot on the left with 17, its width is much less than what we have at 45, right? So we can say that the lower the anode angle, the smaller the effective focal spot, and the better the spatial resolution.
Right, because that spatial resolution won't be as good as the 45.
That's correct. So this one would be worse.
Yeah.
Right. I don't exactly know how much worse.
Right.
And you know, if we were able to do this in the lab and then compare the lines per millimeter on our test tool, then we'd have a really good understanding. But just from this, we could say certainly that the effective focal spot on the right side with the 45-degree angle being larger will give us a lower spatial resolution.
And anodes are made like that? They're made at all different types of angles?
Yeah, they have different angles, right? On average, though, for diagnostic radiography, for different types of special procedures, the angles change. They might be different in mammography. Okay. They can be different in the dental world. Okay, so again, I guess I repeat myself here. Effective focal spot is the point from the image receptor perspective. In this case, it's a line perpendicular to the long axis of the X-ray beam. So it's kind of like your X-ray beam's coming down and your image receptor is this way. So it makes a T. That's where the perpendicular part comes in. But the most important thing on this slide is what's highlighted. And this is an interesting concept. So of note, spatial resolution, and I'll explain this in a second, may be limited if the pixel size is larger than the effective focal spot. Okay, so let's take it from the pixel. The smaller the pixel, the better the spatial resolution, right? But if the pixel size is, let's say, 0.5 millimeter, right, then you can only resolve objects that are 0.5 millimeter or larger than the pixel size itself. Now, if the pixel size, again, is 0.5 millimeter, if you are able to get the focal spot, effective focal spot, because of the line focus principle, if you can get that down to, let's say, 0.2 millimeters, it's not going to help anything because your pixel is larger than that. So the pixel size will limit your focal spot, even if you can get your focal spot to be really, really small. Right? It becomes a limiting factor. Right? So on the exams, though, unless we're specifically comparing pixels, and I talk about this particular type of limitation, it's as simple as focal spot smaller, spatial resolution higher, right? The only change would be is if the focal spot got smaller than the actual pixel size. Then it wouldn't matter. You kind of like hit a brick wall. Whereas further reductions in focal spot size will not matter unless you can get the pixels to be smaller.
Pixel.
Did everyone have a handle on that?
So if focal spot is smaller than the pixel, it doesn't matter.
That's right, because you're limited by the size of the pixel.
So
Yes.
Pixels
that's
shouldn't
also
be
why
larger.
radiologists have so many pixels on their computers, right? Or monitors.
Yeah,
They have better.
yeah. They have really, really expensive monitors, and
Pixels should never be larger.
we'll learn some of these terms next semester where we just really go. If you think we talk digital this semester, just wait, right? But we'll get into things like dot pitch, which is the space between pixels, and the center of one pixel to the center of the next pixel. What is that? Well, now you know it's a dot pitch. That's not on the test though. Next year. Yeah, that's one of the reasons why, right? But here, the other problem is, it's hard to make your focal spot smaller because it means making your actual focal spot smaller too. And then you run into heat issues. So it's tough. We may get to a point where the opposite happens, where you get pixels that are really, really small, but you can't get the focal spot down to meet them. This I have to review again. I don't remember exactly what this is. I mean, it has to do with the fact that the beam is diverging and the effect, there's actually more than one effective focal spot if you think about it. Because when you think of the actual focal spot, it's the point where the photon hits the anode. If you think of this metaphorical effective focal spot, it's actually moving and it's based on where the photons are going. So that's basically what this is saying. Because the beam is diverging, you actually have multiple focal spots, effective focal spots. At different angles, right. With more angle towards the periphery. And as a matter of fact, I didn't mention this to the last group, maybe I should have. The reason why this box is thicker than this one here, even though they're about equidistant from the center point, is that you have anode heel effect going on here, reducing the intensity on the anode side versus the cathode side. But we're going to talk more about anode heel effect in the next couple of slides. There you go. So, short-term memory. I only remember that because I just did it an hour ago. What is the anode heel effect? I'll tell you what it is, and then I'll tell you why it is. So the anode heel effect is a phenomenon where the intensity of radiation, the amount of radiation, is literally higher towards the cathode side of the tube and lower towards the anode. In reality, when we say cathode and anode side, though, it's really kind of like if this is our patient on this table here and their head is to my left, where let's say the anode is on this side, literally cephalically towards the head, you have less radiation, and towards the feet, if this is the cathode side, you have more radiation. And that's how you want to place your patient too, right? Because people get, unless they're all messed up, they get thicker as you go down, right? So that's the definition, that you have higher intensity on the cathode side, lower intensity on the anode side. Now, why? Why does this happen? Right? Because you didn't change your technique. Your technique was what it was. So essentially, because of this angle, you have a situation where part of the overall anode is thicker in one area and not so much in another area. So we call this portion towards the anode the heel of the anode. And it's possible that X-rays that are created that are diverging, and some of them diverge towards the anode side, never make it out. They get stuck. And thus your intensity goes down. Whereas on this side, right, because notice it's not straight, on this side you have a higher chance or a higher proportion of photons that get created and do not get reabsorbed, but actually make it out of the anode. They might get killed by filtration, but at least they made it that far. And the ones that get through the filtration end up actually being part of the primary beam. Right? So there's sort of a spectrum down here. Right? Whereas you might see this kind of like this here, where we have anode over here and cathode over here. And your radiation gets higher as you go towards the cathode and lower towards the anode.
So being that that photon's going that direction, that's why I'm saying it's getting higher towards cathode.
So, right, if you multiply this, right, that means you're going to have a whole bunch more intensity, more photons on the right side towards the cathode, and less on. So that divergence that we've always talked about is not perfect. It's like two shower heads going this way, but one's like stronger than the other, right? When I say stronger, actually more waters come out of one than the other. But this is the trade-off, right? We'd rather give off this slight difference in intensity to gain a smaller focal spot. Because if you take away the anode, you take away this heel, and you take away the angle, then you could have a more uniform beam where where you have more coming out at the same amount across the board, but then you won't be able to take advantage of better spatial resolution. So the anode heel effect in reality is pretty minimal. Rather increase spatial resolution. So the angle of the anode will also have a relationship to the amount of anode heel effect you have. So the more vertical, right, an increased angle of the focal spot is going to give you more anode heel effect. Essentially. Yeah, so the anode heel, so the severity or the amount of anode heel effect you get is based on the angle of the anode. So anode heel is going to happen more often or be more intense when the angle is more vertical, when the angle of the focal spot is reduced. So when angle is reduced, goes down, more anode heel effect. So it's inverse.
More anode, meaning more of the anodes are going to get stuck into the heel,
So
not coming up.
right. So this percentage may change a little bit. right? I could draw these lines a little bit differently. Again, this is something that you can't change because whatever anode is in there, you can't change the angle, right? And when I have duplicated this in the lab, and maybe we do this next semester, I take my digital dosimeter, which some of you may have seen me play with today, others will see me tomorrow. Some of you on Friday have already seen the digital dosimeter with the little laptops. You can take the one particular technique, make an exposure, but put the digital dosimeter far towards the anode side. And then you can take another exposure without changing anything and put it far towards the cathode side and see the radiation difference, right? But it's pretty minimal, right? And now in the digital world, a lot of stuff gets fixed up anyway, right, by the computer algorithms, right? So this was probably done with film, where you didn't have a digital technology to use, because what you have up here is, in theory, so I'll give you the theory first, you should take the thicker part of an object and put it towards the cathode side, right? Because that's where there's more intensity and that's where you need more radiation, like we just said, because the part's thicker. So what you see here, and this, if you're going to see anode heel effect, it's going to manifest itself with long bones. You're not going to see it with a hand, right? You're only going to see it with things that span across cathode to anode. So more likely with like a humerus or tib fib or tib. I said tib fib. Or maybe forearm, right? So what you have here is, if you look here, this area of the elbow is much darker than the one on the right. And that's because it's towards the cathode side and you have more intensity. So you're exposing more than you need to, right? So in theory, you should put the elbow at the anode side where you're getting less radiation so that you can now see it better. And at the same time, towards the humeral head, which is a thicker object, it is towards the cathode side now, right? Because if anode is down here on the right side, then cathode is up here. Well, it even says that, right? Now you're getting a more uniform density. You're better penetrating the head of the humerus. When you try to do this in the lab, it pretty much gets cleaned up. In other words, they both look pretty much the same. It's hard to see this now in the digital world, because in the digital world, the computer lightens this up and darkens that up, right? And kind of fixes it. So the only way to really show this conceptually in the lab is with using the digital dosimeter, right? Because you can't really show it on an image anymore. We can try, right? But much less heel effect. And room 1 almost has no heel effect, right? Even when you use a dosimeter. In other words, the difference between the radiation is very small. Okay, last slide before we talk final exam. So the size of the focal spot, which we said is inversely proportional to the spatial resolution, that part we know. Penumbra is increased with increases in focal spot. We know that's a bad thing, right? And the umbra may be actually reduced. This is what I was trying to explain much earlier when I talked about the donut and the size of the umbra based on the penumbra changing. Maybe one day I'll bring in a donut. Make this work. Am I hungry? Maybe. So what you see here are two different focal spots. We got an A on the left, a B on the right. So we have the larger focal spot size increases the penumbra. So this is the larger focal spot. And you can see our penumbra over here is much larger on the right side, right? This P versus this one on the left, right? But the actual umbra shrinks. That means you have more penumbra and less umbra, right? So our U here is smaller on the right side versus the left side,
And this is all because of the focus process.
right, which is down here. I was hoping it would disappear. You disappear? Disappear for me? I'll do it with my fingers maybe. Right? So here, we're gonna get less penumbra. So we're like taking some of that penumbra away, but we're not changing the overall circumference. If you want, I can kind of draw this out. So you essentially have two circles, right? So here, we have all this is penumbra. Now let's say we go to so this is a large focal spot. We're going to go to a small focal spot, right? So what that's going to do is it's going to give us less penumbra, right, and more umbra. So the umbra actually gets bigger, and the penumbra is smaller, right? So this is bigger, and now this is much smaller,
And the umbra just represents better spatial resolution.
right? And yeah, so this one has better spatial resolution. But the overall size, right, from here to here, right, these two are the same, right? No. Yeah, this is the same. Right, those two are the same. Yes, I can actually write on the screen once in a while. Okay, that makes sense? Yep.
Perfect sense.
Right, so. All right. Let us stop this.